In this video, we'll finish up our discussion of section 14.2 over iterated integrals or double integrals with a few more examples. All right, so we are doing a double integral. We're finding the volume underneath the surface y times e to the xy. And the region is, okay, we can see that it's going to be a rectangular region. This looks like, I think, the last example in this series. We have this box here, right? We can see that 0 to 1 in the x, 0 to 1 in the y. So we are going to be shading over this region. So this is our x and y. Let's label that. We don't want to skip over this drawing out our area because this is what we're going to be doing practically for the rest of the semester. That's going to be super important. All right, so volume-wise, I wanted to find the volume. Okay, I have my double integral. And then I have y, e to the xy, and it really doesn't matter in this case which bound goes first. I like to choose the one with the less variables, so x is 0 to 1, y is 0 to 1. Right? I take my first integral, which is respect to x, so y equals 0 to y equals 1. Right? This integral, x is only in the exponent there. So we'll do a u sub. I'm actually going to write this out. If you can do this, a u sub, and take your integral in the middle of it without showing all this, that's cool with me. Either way, if you want to show every bit of it with our u subs, that's fine. If you want to skip the steps, that is a Calc 2 topic. I am cool with, some people can eyeball it really well, right? This is with respect to x. That's what we have to think about. So this is the derivative of u, xy over here. Taking that derivative with respect to x is just going to give me a y, dx. So notice that is going to take care of the y and the dx. So we're going to get the, I'm not going to take the integral yet here, so we'll do u's now. Okay, so if x is 0, u is 0. If x is 1, we're getting it from here, right? So if x is 1, u is y. And then this and this is taken for du, and so we just get e to the u, du, dy. This makes our integration much simpler. So we get y equals 0 to y equals 1. We didn't touch that, but now we can actually take this integral. It is e to the u, and we want to plug in u equals 0 and u equals y, and then we're going to have one more integral there. Okay, so we get the integral. I can drop my y's because I'm going to have a y in my answer. Be careful with this one. This is e to the y minus e to the 0. This is actually just a 1. I guess we don't need quotations there, but I'll leave it. That is a 1. So now when I take my final integral, I get e to the 0, e to the y, because that just gets that again. And then I have a minus 1. The integral minus 1 is minus y. Then we're going from 0 to 1. So be really careful. It's really easy to fall into that habit of when you're plugging in zeros just to call it 0. I do it sometimes as well, so just be careful. So I got e to the first minus 1 minus e to the 0 minus 0. This is going to give me an e. The e's are gone, I believe, right? No, this is going to be a 1. Careful. So that's a 1. So it's 1 minus 1, so we get e minus 2. There we go. So that is the volume under the curve over that rectangular region. So if that region is the xy plane, z coming out at you, this surface here would be how much volume is underneath the surface and the xy plane. All right, let's do another example. Now notice it's going to start looking probably a little more complicated here. Okay, we have a surface. Our surface is 1 over xy. And then our region, that's what we want to do first, is try to draw that if we can. Right, so we have 0 to e, and then, okay, so let's graph this. X is from y, x equals y is this up and down line, and then it's x equals y squared. My brain, we could think of the parabola that intersects here. If you can, it's a sideways parabola. If not, think about it this way. This is actually the same thing as y equals the square root of x. So they intersect at 1, 1, right? If you plug 1 into both of those, you get a 1. So we are talking about, okay, that's that region. That's the x's are caught between there. And then our y's are going to be caught between 0 and e. Right? So our e, if I remember, e is 2 point something. Checking on my calculator here. If I get it to work. 2.7, that was right. Okay, so it's like up here. So, okay, so we got to try to make sense of this. Y is between 0 and e. And then x is going to be between that. So we get this, I know it's kind of weird to think about, but if e is all the way up there, we still just have this shaded region. Right? Now, the good thing is, with this region, and now I'm kind of doubting myself where that is, let's talk about why we don't really need to envision this one. And the reason is x is defined nicely for us already between two y's. And then also, our y's are nice, 0 and e. I don't really need to find where they intersect because this is defined between two. So the intersection between these two curves is found, but it gets weird up here. That's why we're so iffy. Maybe does it go underneath? Stuff like that. So it may be something like that. So two areas. Now the good thing is, like I was saying, it doesn't really matter because our bounds are defined really nicely. What I mean by that, okay, so let's find that integral. Keep r undefined for a moment. 1 over xy. And then we want to decide, do we want to do x or y first? Well, we definitely want to do x. And that's because x is between y and y squared. Then our dy, because dy is defined 0 and e numbers, not a function. So even though we want to draw pictures every time, the picture didn't really help us for this one. It's really hard to tell what goes on past that. Now, if you want to think about it, you could probably draw this out more, maybe put it in an actual grapher and look to see where it's caught between. But we could figure out the volume or this integral regardless. All right, so we have to take the integral, and then my habit's coming in here. There we go. So we got y equals 0 to y equals e. And then we can go ahead and take this integral. Okay, this is going to be 1 over y x to the negative 1. That's how I think about it. Now we take our integral. Oh, well, we could think about it this way maybe, because if we take x to the negative 1 and go up by 1, we have x to the 0 divided by 0. It doesn't make sense, which is always the indicator for me that when I take the integral of that, it's going to be ln. So this is actually the same thing as this. And then if we take the integral, I don't want to put let's do I, integral, then we're going to get 1 over y ln of x. So taking that integral, we get 1 over y ln of x. And then I know x is y, and x is y squared. Right? The x is between y and y squared, and then I know y is between 0 and e, so that's why I don't have to put an absolute value. Follow that line again. Okay, x is defined by y and y squared, but y's are caught between 0 and e. Those are all positive numbers, so that's why I don't have to put the absolute value. Then I got dy. Okay, I can evaluate that. So write down in my bounds for the outside integral. And then y squared, the y's go in there. I get 1 y ln of y squared minus 1 over y ln of y dy. We could probably put these together. So the integral, and I'm going to go ahead and drop my y's because that's all I have now. This 2 can come out front to make a 2 over y. That's a power rule. So that means I'm going to just write it over here to think about it. I'm going to have 2 over y ln of y minus 1 over y ln of y. The 2 just goes down times, it's a power rule for logarithms. 2 over y minus 1 over y is just 1 over y ln of y. So 1 over y. ln of y dy. This is a u sub, so let's do that. The u is going to be ln of y, because du then is 1 over y dy. Takes care of our whole integral, meaning we get, okay, we should change our bounds too. We're going to plug 0 into here to get our bounds. So ln of 0, oh, wait, we have some weird bound issue here. So maybe we would not want to go that way. Oh, forgive me. My notes, I actually made this mistake and forgot to fix it. So this is actually a 1. So all the way through here, it doesn't change anything till the end. We can't plug 0 into ln, so it didn't make sense. So that's a 1. So please go through and fix all of that. My apologies. I'll fix it in my notes, hopefully this time. I've done it now for a few semesters where that happened. Okay, so the u goes in. Okay, now I can plug in 1. ln of 1 is 0. ln of e is 1. And then everything inside is taken care of, and I'm just left with a u du. So it is u squared over 2 from 0 to 1. And that ends up being a 1/2. So the volume over that region, whatever that region may look like, so this may make more sense then. It would cut this off a bit, 1 to e. So maybe that's why they wanted to cut that off. But I'm pretty convinced that we're going to have like this overlap here in between, something like that. But maybe we should take a look at that on the graph. Regardless, we answered the question. The answer to that integral is 1/2. Okay, got a few more. These are going to get a bit weird where they start defining r given more directions rather than like a set or given bounds or something. All right, so we have this integral. First thing we're going to do is try to draw the region. We want to do this every time. Okay, we have that is y equals 0. We have, I'll do it in green this way, x equals 0. We also have, I have these backwards. All right, so this is y equals 0. This is x equals 0. Okay, how to keep this straight? Because it's a common thing, and as you can tell, like I've done a lot of math in my life, and I still got those mixed up. How you can keep it straight is think about taking a up and down line, right? If it'll let me grab that line. Let me straighten it. Maybe it'll let me move it around then. You take this line and think about this vertical line, and mine's going to be a bit off here. I'm on an iPad. There we go. I think that's straight. And I move it back and forth. This vertical line is always going through the x-axis. So x equals is the up and down. That's how I keep it straight. And then to get it the other way, I just take a horizontal line. I don't know if that's horizontal. I think it clicked in. And I move this up and down my axis. And notice it always goes through the y-axis. So these are y equals. Okay, so with that, we do have another x equals line. So I'll just straighten this out. Try to. Let's see where it clicks. Cool. This is going to be my pi over 2 line. So this is x equals pi over 2. And then we have the graph in the middle of it. That is going to be cosine of x. Okay, I know that cosine of 0 is 1. So I know that the cosine graph starts right there. And then at pi over 2, if I think about cosine at pi over 2 is a 0. So we're talking about the region caught in here. So now they did not give us bounds to think about, but what we want to do in this, let me actually highlight that instead of doing that because I want to draw on here. We can set it up two different ways. In this case, what I like to do is stick typically with whatever the function they gave me, meaning, okay, I can go from here and up. I'm trying to determine what's upper curve and what's lower curve, or I could even do this. Now, this is in the y direction, or x direction, right? And the other one is in the y direction. This is in the x's, right? I would have to have x equals something to x equals something. Careful getting those backwards. It's really easy to do. And this is y equals something, or 0 in this case. This was 0. To y equals something. Now, I have y equals something. That's cosine of x. But this x equals something is going to be an arc cosine of y. I really just don't want to deal with the arc cosine of y and taking the integral of arc cosine. No thanks. So we're going to stick with the y's. So when we set this up, we are going to do y equals 0 to y equals cosine x. We do that first because that puts it in terms like we're going to be plugging x's in. The bounds are y's, so that's dy. And then the x's go from whatever the x's go to. So it goes from x equals 0 to x equals pi over 2. We don't care about the curve anymore because the first part of it is going to take care of the curve. So we have that. That will find the volume under this surface, z equals sine x minus y. We'll find the volume underneath that surface in that shaded region. That is the xy plane. It's like the floor, and then we're going to have mountains or hillside coming out of it at us, like we're looking down on a map. All right, so this integral. What I like about these is they look pretty crazy complicated, but they're most of the time they're nice, easy integrations. So, okay, we'll take our first one. So x equals 0 to x equals pi over 2. All right. The integral of sine x with respect to y is y sine x, right? It's like a constant, minus y squared over 2 dx. And we got to run these bounds. Actually, I should put that there. Y equals 0 to y equals cosine x dx. Now I get to put those in. X equals 0, x equals pi over 2. Let me fix the pi up a little. All right, now plugging y in. Okay, we get sine x cosine x minus, okay, we plug that in, we get 1/2 cosine squared x. And then plugging 0 in is going to give us zeros. That one's okay. Right, this works out just to save some video time, and this is just a U sub for the first one, and then the second one is a, you got to do a, this was remembering that cosine squared x is the same thing, let's make sure I get this right, 1 minus cosine 2x over 2, something like that, I believe. So you do that, this would just be a U sub, let U equal sine, right, and that would solve that. Okay, so this works out, if you want to check your answer, it's 4 minus pi over 8. Okay, so there's an example. A few more now. Try to get a lot of these in. All right, so we have a surface defined by one variable, so don't let that trip you up. So the surface here is z equals 4x cubed, and we have everything defined for us. We should still try to draw this thing because it is interesting because we probably need to know our bounds. So, okay, I have, this is the first one is a parabola shifted to the right, 1. So we'll do this. All right, so it's shifted, so I have the bottom of the parabola. Then I know it goes up 1 on both sides. And then 2, 3, 4 on the sides out of that because 2 squared is 4. So there's my parabola. Try to do my best to draw it. All right, and then the other one, that's a line with an intercept of 3 and a slope of -1. And you can tell that actually hits everything here pretty nicely. So I'm just going to let that correct itself. There we go. And it goes through those points. It's not the best because I drew it. I guess I could have pulled a graph picture. But we have that now. We can see the points here where they intercept. This is 2, 1. And then this is right here is -1, 2. Now, if you couldn't see that and you didn't want to graph it and find the shaded region, or find that, which I totally recommend because we're going to do a lot of stuff with these kind of projections a little later. Now, or bounds really, not projections. If you need help finding that point of intersection, you could just set x minus 1 squared equal to negative x plus 3 and solve. So it's a quadratic problem, but you can find those 2 points. Okay, so I have things defined in y already. I don't want to change the x's, but finding those intersections will give me my x values. So I have that thing is equal to, all right, I'm going to leave my 4x cubed. And what I should do first is my dy, since I have both of them here. Now be careful though, because it is going to be the y equals x minus 1 squared on bottom, and that's because the curve here is below, right? And then on top is the negative x plus 3 because it's above. We're talking about this region. I guess we could shade this. Oops, I erased it instead. Talking about the region enclosed in here. So it's the volume above or below the surface of this region in space. Okay, so we have that. Now we have to do our x's. And all we have to do is look at the actual graph. X goes from negative 1 to 2. I'll show you where I picked up those values. Right here and right there. The x's from the point to point. The curved part is taken care of with our y's. All right, so this is not terrible integration. It's pretty quick. So we have that with respect to y is 4x cubed y from, okay, y equals x minus 1 squared, y equals negative x plus 3, and then dx. All right, we could plug all that in. I'm going to save us some time on the algebra. This ends up being, I'm going to go ahead and drop my x's because that's all I'm going to have now. If I plug in each one, here I'll actually write that out, 4x cubed times negative x plus 3 minus 4x cubed times x minus 1 squared dx. We're going to want to multiply all that out. What we get when we do that, and you should do it and double check with mine. Right, let me see, one sec. Okay, so we get I'm trying to, negative 4x to the fifth, right? Plus 4x to the fourth, right? And then a plus 8x to the third. I think that's it. Yeah, dx, right? I integrate all that. Okay, so I get negative, it's going to be negative 4/5 x to the fifth. Something happened in here. I don't think that's a 5. I think there's an error in here. Let's just do it. I'm going to do it by hand because I think my notes are off. So let's do this. I'm going to simplify all that for us. We get negative 4x to the fourth plus 12x cubed minus 4x to the fourth. Oh, wait, that's going to square. We're going to square that out. So we get x squared minus 2x plus 1 dx. There we go. Then we got negative 1, 2. Okay, combining, I guess I'll multiply all that out. I'm going to do it right under because I'm running out of space. Plus 12x cubed minus 4x to the fifth plus 8x to the fourth minus 4x to the third. Right, maybe it was right. Okay, so I have a negative 4x to the fifth. That's that. Okay, and then the force, I got plus 4x to the fourth plus 8x to the third. Yeah, that was right. I was just wrong in my notes. Okay, so from here now, we get to take our integral, and we get negative 4 over, remember, we go up by 1, x to the sixth, and divide by our new one, plus 4/5 x to the fifth, right? And then plus, okay, we go up by 1, we get 2, x to the fourth, and then we're running this from negative 1 to 2. This is going to work out to 72 over 5.